Let me now bring back the electronic systems block diagram that we discussed in the first class, and then we have been repeatedly seeing this block diagram at various points in our earlier discussions. So this is the entire electronic systems block diagram. We are in this part. We sensed using some sensor, some transducer, and the output of the transducer is an electric voltage or current, and that is passed through a zero and span circuit, so that you get an output from the zero and span circuit which is compatible to be processed through an A to D. If there are offsets, you are trying to remove the offsets. You are trying to correct the slope of the input-output relationship in such a manner that you are able to utilize the entire resolution of the A to D. So that's the objective. Now after the zero and span circuit, you can take the signal towards the A to D, but before you take the signal and give it to the A to D, you need to pass it through a filter. And after the filtering, you need to you can give it to the A to D for converting it into the signal into the digital domain. But why do you need the filter? The filter is called anti-alias filter, and as the name suggests, the filter tries to remove aliasing. Now what is this aliasing and where does it come from? So let us look at that and incorporate the filter in this analog signal processing block, and then we will be able to give the signal from the transducer passing through the zero span, then the anti-alias filter, and into the A to D for conversion into the digital domain. Let us now discuss the anti-alias filter and see what it is. What is the concept behind this? And then later we will design a simple popular anti-alias filter which will resolve the aliasing problem. So what is this aliasing? Now let me go into the frequency domain. This is the amplitude, and the x-axis is omega. This is the frequency domain. I am taking the frequency axis as the x-axis. It's not the time axis. So in the frequency domain, so you will see that the base band of the signal has several frequency components. So the frequency component is distributed continuously, and let us say it is something like this. So this is, so you mean that you see that there are different frequency amplitudes from 0 to omega m. Omega m I am using it as a modulating signal. So let me call this a modulating signal. Omega m is the maximum value of the baseband signal. Beyond it, there are no values for this, no frequency components for this baseband signal. So the composition is that it has various amplitudes of various frequency components from 0 to omega m. Beyond omega m, it is not there. So let us consider that. We call it a band limited signal. It is band limited to omega m. Now let us say that we sample this. We have to pass it through an A to D, right? So let us sample it. If you sample it, you will see that there is a duplication of this baseband signal shape on the frequency axis. So let us say that we sample it at a carrier frequency called omega c. So let's say at omega c I will sample it. This is the frequency at which I will sample it. The moment you sample it at that, you will see that there will be a duplication of this baseband signal around this sampling point. So it will come in like this, and you will have side bands which is omega C minus omega m, because this is still continuing to be omega m on both sides, on omega c plus omega m. And this will happen at every omega c integral value of omega c. So at 2 omega c, there also you will have that. So let us say if I extend the x-axis, so at 2 omega c, there also you will have a duplication of the baseband signal. And on the minus side also, minus 2 omega c, you will see that duplication happening. So let me mark this as omega m. This is the band limit for this baseband signal. And this with respect to the carrier frequency value, you will see this is also omega m. Now what happens if I reduce the value of omega c for the same baseband signal, modulating signal? What happens if I keep reducing the value of omega c? So you will see that this is moving closer to the modulating signal shape. So let us see that. So let me erase this and let me remove this also, so that we have, when you are moving, it becomes clear. So I am moving this, I am reducing the sampling frequency or the carrier frequency, I am reducing it, I am continuously reducing it, and you see that this keeps moving closer and closer, and at this value, omega c, you will see that just about is twice this band limited baseband value omega m, that is 2 times omega m. So omega c at this point is 2 times omega m, and this is at the boundary of the sampling theorem, the Shannon sampling theorem, which says that sampling frequency should be equal to greater than the modulating signal bandwidth, which is omega m here. So when omega c is greater than omega m, there is no problem. There is no overlap. So no issues. But what if omega c is less than 2 omega m? Then you have this problem of aliasing coming in. So if I move it still to the left, which means that I am reducing the sampling to less than 2 omega m, so you see this overlap. So if I take now some frequency less than omega m, I will have 2 possible points. Should I take the component corresponding to the baseband value, the higher frequency component of the baseband value, or should I take the component corresponding to the omega c sideband? Which one should one take for reconstruction? So this is the dilemma, and this is a problem where you will not be able to resolve, and you will not be able to reconstruct the original signal because of this aliasing. The information is lost. You won't know whether to take this or this. So these are the alias points, and you call this as an alias. And the signal reconstruction under such cases is not possible even according to the sampling theorem, Shannon sampling theorem. So it is important that we have the modulating signal band limited to less than omega c, which is the sampling frequency, by 2, omega c by 2. All the band limit should happen within that. And the modulating signal should not have any values or frequency components beyond omega c by 2. If it is there, it should be attenuated. That is the job of the filter. So if I consider anti-alias filter will attenuate all frequency components greater than omega c by 2 in the baseband signal or the modulating signal. So if I take the frequency axis, and let us say we have a modulating signal like that, and there is a tail, there is a long tail with respect to frequency components. Let's say this is your omega c, and here is omega c by 2. So this is the limit boundary of the sampling theorem, and I should not have any baseband signal, any modulating signal component, frequency component beyond that. So I have to attenuate that. Likewise on this side also. So I should have a filter in this manner which will eliminate all the frequency components beyond omega c by 2 and pass only the signals which are less than omega c by 2. So this filter, such a filter is called the anti-alias filter. So anti-alias filter, the sharpness of this anti-alias filter depends upon the type of the modulating signal and the sharpness of the modulating signal and the frequency components towards the boundary of the sampling and the bandwidth. So if the amplitudes are smaller, I can still go for a slope which is not as steep as this, which means that I can go for a lower order filter. And for much simpler systems where you have very less number of frequency components, and if the amplitude at the boundary of the sampling theorem is small, then I can go for even second order system or third order system. So I will demonstrate to you a simple filter, a second order filter called the Sallen-Key filter. You can concatenate the Sallen-Key filter, several of them, to increase the order of the system. Let us try to understand the Sallen-Key filter, which can be used as a second order anti-alias filter. So it's an active filter based on op-amp. So it has two RC. So there is one R and there will be a C here. There is another R and a C to ground. And this point is connected to the op-amp plus input, high input impedance. And this is in unity follower mode like this. This point is connected to a capacitor and connected to the output. So this is Vi and this is V0. Let's say this is R1, R2, C1 and C2. So let us try to get the input-output relationship. Let me name some node points here. So this is V0. So there is a virtual ground. So therefore this node point will be also V0 value. And this I will call it as Vx, an intermediate value. So at this point, if you apply Kirchhoff's KCL, current law, Vi minus Vx divided by R1 will be the current through this branch, which should be equal to this branch current and this branch current. So Vx minus V0 divided by 1 by SC2 is this branch current, and this branch current will be Vx minus V0 divided by R2. So this is one equation that you have. Another equation, you can apply KCL at this point. So here the current into the plus terminal is 0. So therefore the current in the R2 branch and the current in C1 branch will be equal. So therefore Vx minus V0 divided by R2 should be equal to V0 divided by 1 by SC1. This is the second equation. So you have two unknowns, Vx and V0, and we need to find V0, Vx and two equations, and therefore it is possible. From this equation we can find out that Vx in terms of V0 can be written as 1 plus SC1 R2 into V0. The value of Vx in terms of V0. So using this and this, for equation 1, you should be able to obtain the input-output relationship. Try to do that. I will write down the final equation, which is of the form 1 by R1, this R1, 1 plus S R2 C1 into R1 plus R2 plus S C2 R1 R2 by R1 R2 minus 1 plus S C2 R2 by R2. So this is the complete equation. Now to this equation, so normally the popular Sallen-Key filters apply some constraints to the values of R1, R2 and C1, C2. So the constraint that is applied is set R1 is equal to R2 is equal to R. These both will be equal, and set C1 is equal to C and C2, this C2 is equal to 2C. So if you set these values, then we get some nice damping properties. So let me illustrate that. And substituting these values in the input-output equation, so you will land up with 1 by R, 1 plus SRC into 2R 1 plus SRC by R square minus 1 plus SR into 2C by R. You can further simplify that and you will finally get it in this form: 2S square R square C square plus 2SRC plus 1. You can also express it and divide by 1 by 2 R square C square S square plus S by RC plus 1 by 2 R square C square. This is V0 by Vi. This is the relationship that will be of some use to us in designing. And omega C at the cutoff frequency, from the natural frequency you get omega C square is equal to 1 by 2 R square C square, and therefore omega C is 1 by root 2 RC. So you can decide on the cutoff frequency by designing the value of RC appropriately. And this value is 2 tau damping ratio into omega C, which is equal to 1 by RC. Omega C is 1 by root 2 RC, and therefore the damping ratio is 1 by root 2 always. If you choose R1 is equal to R2 is equal to R, C1 is equal to C, and C2 is equal to 2C. So this plugging these values for any given cutoff frequency, you will get a second order Sallen-Key filter with damping ratio of 0.707 or 1 by root 2. So use this, interpose this between the zero span circuit output and the input of the ADC. So you have the transducer, the output of the transducer connected to the input of the zero span circuit, output of the zero span circuit connected to the input of the anti-alias filter, which is the Sallen-Key filter in this case, and the output of the Sallen-Key filter or the anti-alias filter is connected to the input of the ADC pin of the microcontroller.